بشكر مجددا البروفيسور يوسف أجري زرقاني على تقديم محاضرته. الآن ندعوكم إلى استراحة قصيرة مع القهوة متزامنة مع السيشن أوف بوستر، تليها مباشرة انطلاق جلستان سيسيون 1 سيسيون بي. سيسيون 1 مع أستاذ نميسي، سيسيون بي خاصة بالرياضيات في القاعة المقابلة مباشرة. فليجهزوا الطلبة أنفسهم. شكرا، تفضل.
بسم الله الرحمن الرحيم. نرحب بالضيوف في الاسيسيون هذه IAM'24. Donc on commence par le first speaker, Anis Abdelifrad, who will be discussing his research titled Sensor Fault Detection based on New Symbolic Covariance PCA. Donc, تفضل.
Good morning, everyone. I'm pleased to present our work titled Sensor Fault Detection based on New Symbolic Covariance PCA. This work, this research includes innovative approach to enhancing the sensor fault.
Please, سامحني, we make a pause, juste ما يدخلوا الأودينس ومن بعد. Bismillah ar-Rahman ar-Rahim. Donc je m'excuse pour vous interrompre. On reprend le first speaker. Donc تفضل.
Good morning, everyone. I am pleased to present our work entitled Sensor Fault Detection based on New Symbolic Covariance PCA. This research interviews an innovative approach to enhance sensor fault for based on the new advanced PCA, contributed to system reliability. The presentation is started as below. We begin with an introduction and a review of principal component analysis and its constraint. Next, we address data uncertainty description and symbolic covariance PCA as an extension of PCA. Then we will discuss SCPCA limitation and its application in fault detection based on ESP. Finally, we conclude with the practical application of CPCA in a greenhouse prototype system. Today, companies aim to stay competitive and improve product quality and quantity by adopting performance process in their factories. This process including intelligent developed technologies such as intelligent sensor, complicated machine, and actuator. The development technologies required strategies for diagnosis and monitoring to ensure safe process and avoid accident and protect operator and equipment and avoid losing productivity. A strategy for diagnosis and monitoring involved three main task: detecting, isolating, and identifying faults. The first fault detection determines the presence of the fault in the system. Fault isolation pinpoint the cause of the fault. And fault identification identifies the size of the fault. There are two methods are used for developing monitoring and diagnosis strategies. We have the first one, analytical approach. This approach relies on mathematical models to represent system expected behavior and requires detailed knowledge of the system dynamics and physics. The second one, data-driven approach, uses heuristical data to train algorithms and represent the behavior of a system and relies on the AI methods such as machine learning and statistical methods like PCA. In this work, we will address multivariate statistic method known as the principal component analysis or PCA for monitoring and diagnosis system. Principal component analysis is the way they use technique in industrial system for process monitoring and the fault diagnosis, due its ability to efficiently handle the large data sets. It's not the algorithm of this technique realized using 5 steps. The first one, grouping the data set in the matrix X, then normalizing the data matrix X. That means scaling and sundering the data. The third, we calculate matrix covariance using this formula. After that, we calculate or we compute the eigenvalue and eigenvector of the covariance matrix. Finally, we estimate the data matrix using constructed model. Despite its utility, PCA has inherent constraints that may affect its performance and suitability of modeling phase for process monitoring and fault diagnosis. The first one, linear assumption. PCA technique assumes that the relation between variables are linear. It may not capture complex non-linear correlationship in the data. In this construct, there are many techniques that extend PCA to handle the data. Non-linear relation between the data. The second one, sensitivity to data uncertainty. PCA technique assumes the data is accurate and reliable. If the data set includes a certain measurement, such as imprecise data, sensor data, it can destroy the covariance structure and negatively impact the principal component. In this case, there are many techniques that developed for handle data uncertainty. We have mid-point and radial PCA, CPCA, and CPCA. Data uncertainty description. Real-world application data often exhibits the uncertainty due measurement error, incomplete information, or inherent variability. To analyze and interpret uncertain data effectively, it's essential to represent this uncertainty in a structured manner. We have three representations of uncertainty data in the literature. We have interval and histogram and distribution. In our work, we represent the data as data uncertainty using interval representation. Although interval data is constructed, it's essential to extend classical PCA to interval PCA to take into account all information contained in the interval data. This approach helps establish a model that prevents false detection while maintaining sensitivity to deviation. A CPCA is a variant of interval PCA that was developed to address data uncertainty in the model. The algorithm of this technique, it's the same of classical PCA, but the unique or the only difference is the construction reside in the construction of interval data matrix and normalization of interval matrix and calculation matrix and calculate covariance matrix. Matrix covariance matrix calculation it's performed by this formula. The covariance matrix computed using the SPCA approach maintains the same structural form of the classical PCA covariance matrix but does not respect their mathematical properties depending on the data normalized. When the data is normalized to zero mean and unit variance, the diagonal element of covariance matrix are not the same as given by the unit variance. The other element of covariance matrix can have value outside the range of -1 to 1. The covariance matrix of m variable does not equal its corresponding correlation matrix. This drawback limits the application of this method for real application and can lead to misdiagnosis in fault prediction cases. The newly adopted SCPCA method seeks to address the limitation of the original SCPCA approach in detecting sensor fault in the presence of uncertainty. The conventional SCPCA covariance is given by formula. We call writing this formula rewriting this formula. That means we developed this formula. باش درنا هاد الفورمولا. Therefore, the sample covariance matrix become like this formula. After establishing the SCPCA model that represents normal behavior process, various statistic indices are used for monitoring phases. The most commonly used statistic for anomaly prediction is a square prediction error. SPE is computed at instant k as follows by this formula. Normal behavior of process must be verified SPE less or equal the threshold. The threshold is defined by this formula. When dealing with interval value data, the indicator SPE must be adapted to fit interval value PCA model. This means extended statistical measure SPE to appropriately handle the variability structure within intervals. The ASPE for interval data is defined at instant k as follows by this formula. Application to greenhouse prototype system. Our greenhouse prototype system was located in Biskra province, Algeria, an area known for its middle desert winter. It's designed as a nursery to grow seedlings until they are ready to be planted, as shown in figure 1. The prototype was equipped with 9 sensors and we use only 7 variables. The database recorded winter condition every minute for 5 days in January 2019, resulting in 7,200 data points. After a total of 6,200 samples were used for model training, and while 1,000 samples were used for model testing. Uncertainty was incorporated with a 10% variation range for each variable, serving as the interval radius. In order to demonstrate the effectiveness of new SCPCA approach, we will compare its performance with that of SCPCA and the conventional SCPCA method. The figure 2 shows the interval data of internal temperature and external relative humidity with the estimated using SCPCA, CPCA, and new SCPCA models. The detection index of ESP-based SCPCA. The figure 3 show evolution for SCPCA ESP-based on SCPCA model and CPCA based ESP-based CPCA and new and ESP-based and new SPCA and the normal condition. The index, the detection index of the ESP-based on SCPCA approach indicate that the system is poorly modeled when compared to ESP-based on SCPCA and the new SPCA methods. Additionally, both versions of SCPCA exhibit and disable false alarm rate. However, the new SCPCA is more effective than older version. Imagine false alarms caused by uncertainties. Figure 4 shows the system in the case fault, which has been injected by a real fault since the instant 500 minutes of the testing phase. The magnitude of the fault injected represents 25% of the range of variation in the internal temperature sensor. The SPC and the ESP and the detection index based on the new SPCA and the CPCA approach required only a lower magnitude of fault to continuously detect deviation in the system. In contrast, the ESP based on the SPCA required a high magnitude fault. Conclusion: the new advantage of the new SPCA is the respect the properties mathematical of classical PCA covariance matrix when data is normalized. This leads the new approach to be more effective against false alarm caused by uncertainties and more sensitive to fault detection than its previous version and classical PCA. Limitation of the new SCPCA does not take into account all information present in the interval data. As a result, the construct interval model PCA is not robust enough to handle false alarm caused by uncertainties and lacks sensitivity to deviations. Perspective: the issue discussed in this method can also be applied to other interval PCA approach that does not adhere to the mathematical properties of simple covariance matrix of the classical PCA, such as mid-point and early PCA. Merci pour votre attention.
Thank you for that presentation. And let's move on to the question session for this presentation. We welcome your questions and reflections. Est-ce qu'il y a des questions, des opinions? Sinon, je vais poser une question. Les capteurs, les DK, ce sont des capteurs de température ou d'humidité ou non? Les capteurs.
Les capteurs, bon, اللي يهمنا هو la nature du capteur. Est-ce que la valeur fournie quantitative ولا la nature واحدة خلاص؟ c'est-à-dire حنا اللي يهمنا الكابتور اللي عندنا la nature تكون quantitative، c'est-à-dire des valeurs réelles. دونك في لو كا هنا كاين دي كابتور، عندنا 9 كابتور، حنا خدمنا ب 7 كابتور، لي دو الاخرين باسكو ماهمش لينييرمون كوليري افيك لي زوطر. الوغ لي كابتور اللي عندنا تمبيراتور، ليميديتي، لا بريسيون، لا فيتاس دو فون، وكاين منهم دوبلي.
تما ما حددتيش لا ناتور تاعهم برك اسكو لو موديل كيفاهم هاد
بون حنا نسيت كيفاش نموديليزي، حنا نموديليزيو les systèmes utilisant la modélisation de type boîte noire. c'est-à-dire un système, modéliser un système, utiliser les entrées et sorties seulement, mais يعني ما نحوسوش على l'entrée يعني اش كاين في الانتيريور تاع السيستم.
داكور. دونك بغض النظر على الطبيعه تاع الكابتور في حد ثم بوكو بليس تمكن لي دوني.
Voilà,
بغض
exactement.
النظر على الكابتور في حد. داكور. Est-ce qu'il y a d'autres questions? Sinon, on vous remercie encore une fois et on passe à la présentation suivante. Je donne l'attestation.